Okay, so we are now interested in solving non-homogeneous linear nth order differential equations with constant coefficients. So to be clear, the only difference between this section and the previous section is that these differential equations will be non-homogeneous, meaning the right-hand side will not be 0. It'll be other stuff. All right, so the key again being that g of x on the right is no longer going to be 0. The method entails actually solving the associated homogeneous differential equation. In other words, as a very first step, we're going to replace g of x with 0 because we know how to solve that. And that will be a big part of the general solution. However, once we've done that, then what we do is we look at the form of g of x, and we're going to find a particular solution out of the form, meaning like the structure of what g of x looks like. So most of this section is actually that particular step, right? That's the thing that's new here. But let's write down an outline of the method. So the associated homogeneous differential equation would be exactly the same left-hand side, but the right-hand side, of course, being 0. The general solution to this homogeneous part we will call the complementary solution. And it'll be denoted y with a subscript c for complementary. And of course, this complementary solution will look just like the solutions from the last section. So a linear combination of linearly independent fundamental solutions. So a constant times a fundamental solution plus a constant times a fundamental solution, etc. Okay, so that gets us that far. The next thing we do is we put our attention on the g of x. And using the structure of the g of x, meaning whether it's trigonometric or exponential or polynomial, we're going to predict a trial particular solution, which we will call y subscript p. All right, once we have determined that trial particular solution, then the general solution to the non-homogeneous linear nth order differential equation will simply be, by superposition, the sum of the complementary solution and that particular solution that we found. Okay, it's probably not evident why that's the case yet, but I believe if we start looking at examples right away, it should start to become clear why this method actually works to produce the general solution. So let's go and look at our first example. All right, so here you can see we have certainly a non-homogeneous linear differential equation with constant coefficients. So according to the technique suggested a moment ago, we should find the complementary solution. So let's do that first. Okay, so we're going to need the associated homogeneous differential equation, which is y double prime plus 2y prime minus 3y equals 0. So for the moment, we're kicked into section 4.3, where we're just solving this homogeneous differential equation. So we know how to do that. We need the auxiliary equation. And we'll just solve this guy, which factors. So we get m plus 3, m minus 1 equals 0, giving us m equals negative 3 or m equals 1. So our complementary solution is going to be c1 e to the negative 3x plus c2 e to the x. Okay, so that's the complementary solution. Now, we are using the word solution in there, but it's not a solution to the original differential equation. In fact, if you substituted it into the original differential equation, you would get 0 on the right-hand side and not that polynomial. So the next thing to do is to find a trial particular solution. So, okay, what is the form going to be? Now, here what we do is we look at the right-hand side of the original non-homogeneous differential equation, and we ask ourselves, what type of function where if you take it and some of its derivatives and you sort of add them together and multiply by constants will give a polynomial like this? So to make the point clear, let's first give a bad answer to this. Let's suppose we figured, hey, maybe the particular solution is like sine of x. Okay, but we know that the first derivative of sine is cosine, and the second derivative of sine is negative sine. So how could it be, if you look at the original differential equation, that the left-hand side would obviously be comprised of sums and differences of sines and cosines? How could that possibly equate to a polynomial on the right-hand side? So I hope you can see that that's just a bad decision for a trial particular solution. In fact, because the right-hand side is a polynomial, a second-degree polynomial specifically, we should let the form of our particular solution be kind of a generic quadratic here, ax squared plus bx plus c. You know that the first and second derivatives of this quadratic will themselves be polynomials, and so if you go and plug those into the original differential equation, you're going to get a big mess of polynomials on the left, which would actually equate to a polynomial on the right-hand side. And you'll have, of course, on the left a bunch of a, b's, and c's, and you can solve for those missing coefficients, giving you the precise values of a, b, and c that we need. So returning to our trial particular solution here, let's take its first derivative, which is 2ax plus b, and let's take its second derivative, which is 2a. And now we're going to replace these forms in the original differential equation. So here's the original differential equation, and now we're going to replace y double prime with the trial particular solution's yp double prime. So this is going to be 2a, and y prime will get replaced by 2ax plus b, and y gets replaced by ax squared plus bx plus c, and the right-hand side is that thing. So now, using methods that are reminiscent from when you found the coefficients from partial fraction decomposition, you can determine what capital A, capital B, and capital C are. So let's distribute and combine by power of x. So we have 2a plus 4ax plus 2b minus 3ax squared minus 3bx minus 3c is equal to this quadratic. So left side we have negative 3ax squared, and then we have 4a minus 3bx, and then the constants 2a plus 2b minus 3c. Okay, so equating the coefficients, we can see that negative 3a is equal to negative 15, and this tells us that a is equal to 5. We can see that 4a minus 3b, the coefficient of x on the left, is equal to 20. But we know a is 5, so this is 20 minus 3b is equal to 20. Well, that tells us that b is equal to 0. That's very nice. And finally, equating the constant terms on the left and right, we have 2a plus 2b minus 3c is equal to 12. Well, 2 times a, we know a is 5, so 2 times a is 10. We know b is 0. So we can use this to find c. Negative 3c is 2, so c is equal to negative 2/3. Okay, so the particular solution is yp, so that was ax squared plus bx plus c. So in this case, that's 5x squared plus bx, well, that b is 0, plus c, so minus 2/3. Okay, now the first thing to note is that unlike the complementary solution, this particular solution actually is a standalone solution to the original differential equation. And of course, what's remarkable is the general solution by superposition is just the sum of the complementary solution and the particular solution. Okay, and you could verify this if you wanted. We're not going to, because this is correct. Let me give a quick sketch for why we can accept that this method actually works without fully proving it. So here's the original differential equation. Now we claim that yc plus yp is a solution. So, okay, well, the first derivative is yc prime plus yp prime, and the second derivative is yc double prime plus yp double prime, because that's just how derivatives work. So if we go and plug in these pieces, we're going to get yc double prime plus yp double prime plus 2 yc prime plus 2 yp prime minus 3 yc minus 3 yp. And this is going to give us yc double prime plus 2 yc prime minus 3 yc plus yp double prime plus 2 yp prime minus 3 yp. And we know that since yc, the complementary solution, is the solution to the associated homogeneous equation, that means that literally this big chunk here evaluates to 0. And what about this? Well, we know when we plug the particular solution into the left-hand side, by our judicious choice of A, B, and C, it's going to generate that right-hand side. So we're going to get negative 15x squared plus 20x plus 12, which is the right-hand side of the differential equation. So that should convince you that yc plus yp is indeed the general solution. All right, so here we have a clearly non-homogeneous linear second-order differential equation with constant coefficients. So we're going to just follow the method we've been doing. So the first thing we should do is find the complementary solution. Okay, so we need the associated homogeneous differential equation. So that would be, of course, y double prime minus y equals 0. And we'll just solve that by solving its auxiliary equation. That one's not too bad. We get m is plus or minus 1. So that means that our complementary solution is c1 e to the x plus c2 e to the negative x. All right, so we'll come back to that. And now we'll put our attention on the particular solution. So again, we need to be very careful selecting the form of our trial particular solution. And this time, we can see that the form's trigonometric. It's going to involve sine. So the most general form when you have sine of something is to include both sine and cosine in your trial particular solution. So we're going to say some unknown coefficient a times cosine of 2x plus capital B times sine of 2x. So this would be the case regardless of whether or not the right-hand side were a sine or a cosine, or even if both of them were present, we would still let this be our trial particular solution. All right, so let's take all the derivatives we need. In this case, it's a second order, so we'll take two derivatives. So we know that this is negative 2a sine of 2x plus 2b cosine of 2x. We'll take one more derivative, and we're going to get negative 4a cosine of 2x minus 4b sine of 2x. So now we will replace these particular solutions in the original differential equation. So there's the original differential equation, and we can see that we're going to get negative 4a cosine of 2x minus 4b sine of 2x minus y, and so y would be our a cosine of 2x plus b sine of 2x, and that's equal to the right-hand side, which is 6 sine of 2x. So again, we just need to determine what the undetermined coefficients are here, capital A and capital B, of course. I hope you're starting to see why this technique is called undetermined coefficients. All right, so let's get the cosines together and the sines together and see what we're working with. All right, well, we've got negative 5a cosine of 2x, and we have negative 5b sine of 2x is equal to 6 sine of 2x. Okay, so in this particular one, we can see that a is equal to 0, and we can see that negative 5b is equal to 6, making b is equal to negative 6 over 5. So that means that our particular solution, which has the form a cosine of 2x plus b sine of 2x, is going to equal 0 times cosine of 2x, so we'll just skip that, and negative 6 over 5 sine of 2x. So there's our particular solution. Okay, so that means that the general solution, which is the complementary solution plus the particular solution, is this guy plus, now we'll write it as minus, I guess, 6 over 5 sine of 2x. And there we are. Okay, so here again, we have a non-homogeneous second-order linear differential equation with constant coefficients. Let's do what we've been doing. First step would be, of course, to find the complementary solution. So the associated homogeneous equation is y double prime plus y is equal to 0. And we actually solved this homogeneous equation in the last section. And we got a solution of c1 cosine of x plus c2 sine of x. Now let's find the particular solution. Okay, so of course one of the most interesting parts of this whole lecture is setting up that trial particular solution, the form with the a's and b's and so on. So what you want to do is kind of get the most general version of whatever's on the right-hand side. Now, the right-hand side here is kind of in two parts. It does have three terms, but the first two terms can be considered one part, which is this polynomial part here, 2x minus 1. And the most general version of that, we can just say, is ax plus b. Now, this last part here is 3x e to the x. And what do we have? But we have a linear multiplied by an exponential. So we need to represent that by the most general linear form, which would be cx plus d. We have to use new letters. We cannot reuse any letters, so we have to go all the way to C and D at this point. And then e to the x. And that would be our trial particular solution. Quick note, your book avoids the use of capital D in its trial solutions. So actually, if your book were doing this example, it would go A, B, C, and capital E. And it avoids the capital D because of its use as the differential operator. But I don't find that to be quite a huge conflict, so I tend to just go with the capital D, but you can use whatever letters you want. So let's take our derivative, which will be A plus, and then by the product rule, the derivative of cx plus d, which is c, times e to the x, plus cx plus d, times the derivative of e to the x, which is e to the x. We will take one more derivative. Of course, we're going to get c e to the x plus, once again, the derivative of this thing, which we know to be c e to the x, plus cx plus d e to the x. We can combine those two first terms to get this and this. Okay, so now let's go and substitute these particular forms into the original differential equation. So the original differential equation was this thing. So we're going to get y double prime, which is 2c e to the x, plus cx plus d e to the x, plus y, which is ax plus b plus cx plus d e to the x. And that's equal to the right-hand side, which is 2x minus 1 plus 3x e to the x. Okay, so we have our work cut out for us. We need to determine the values of these coefficients, a, b, c, and d. So let's combine by power of x and just the exponential as well. So we have 2c e to the x plus, let's distribute. Actually, let's notice that we have two copies of this cx plus d e to the x. So we can distribute right away. We say 2cx e to the x plus 2d e to the x plus ax plus b. And that's equal to 2x minus 1 plus 3x e to the x. So again, we have, let's start with this guy. We've got 2cx e to the x. That's the only one of its particular brand. We have 2c plus 2d e to the x plus ax plus b is equal to 2x minus 1 plus 3x e to the x. I think we're ready to equate coefficients now. So we can see that the coefficient of x e to the x on the left, which is 2c, must match the coefficient of x e to the x on the right, which is 3. This tells us that c is equal to 3/2. We can see that the coefficient of e to the x on the left, which is 2c plus 2d, must match the coefficient of e to the x on the right. But there is no e to the x term on the right. So 2c plus 2d must equal 0. Okay, but we know what c is. C is 3/2, so this is that. And looks like we're going to get d is equal to negative 3/2. So we've got c and d. And a and b are pretty easy. Look at that. We can see that a is equal to 2 right away. And we can see that b is equal to negative 1 right away. So we have all four, a, b, c, and d, which means we have our particular solution. So our particular solution, remember the form of it. It was ax plus b plus cx plus d e to the x. So this is going to be 2x minus 1 plus 3/2 x minus 3/2 e to the x. Of course, the general solution is the complementary solution plus the particular solution that we found. So complementary solution was c1 cosine of x plus c2 sine of x, and then plus the particular solution. So 2x minus 1 plus, and in this type of situation, it's generally favorable to distribute. So we have 3/2 x e to the x minus 3/2 e to the x. And there we are. Notice that there still only are two parameters here, right? This is still a second order differential equation, so we would expect no more than two parameters. And those parameters emerged way back when we were finding the complementary solution. The particular solution doesn't have parameters. It's just added on. It's very specific. It's particular. All right, well, this one doesn't look too bad. So let's see. First thing we should do is, of course, find the complementary solution. But this has the same left-hand side as one we worked out earlier. So we know the complementary solution here is going to be c1 e to the x plus c2 e to the negative x. And this is from an earlier example. Okay, so all we need is the particular solution. So looking at the right-hand side, 3e to the x, one could easily decide that the trial particular solution should be a e to the x. All right, well, let's see what happens. We're going to get y prime is a e to the x, and we're going to get our y double prime, which is a e to the x this time. Okay, so plugging those into our original differential equation, we're going to get y double prime, which is a e to the x, minus y prime, which is a e to the x, is equal to 3e to the x. So simplifying the left side, we get 0 is equal to 3e to the x. Okay, so something definitely went wrong here. And the issue is that our trial particular solution is already represented within our complementary solution. The trial particular solution needs to be linearly independent from all the fundamental solutions determined from the complementary solution. So no problem. If you think back to one of the moves from the last section that we used to handle that type of issue, you might consider putting in a factor of x. And that is in fact exactly what we need to do, and that's going to work. And if that were also represented already in the complementary solution, then we would just introduce another factor of x, making it x squared, or x cubed, or x to the fourth, or whatever the lowest power of x is that you need in order to guarantee that this particular solution is independent of what's already represented in the complementary solutions. So here, x to the first power is good enough. Taking that first derivative, this is not as easy as it was a minute ago. We need the product rule. I think we'll be okay though. All right. So now we're going to take those things and stuff them into the original differential equation, and we are going to get finally something that makes sense, and we'll be able to determine what that a value is. So y double prime, this is 2a e to the x plus ax e to the x minus y, which is ax e to the x. That's all going to equal 3e to the x. All right, well, this is really nice because those terms completely cancel out. So we're going to get 2a e to the x is equal to 3e to the x. This tells us that 2a is equal to 3, and therefore a is equal to 3/2. So our particular solution is 3/2 x e to the x. And therefore the general solution, which is simply the sum of the complementary and the particular solution, is c1 e to the x plus c2 e to the negative x plus 3/2 x e to the x. And there we are. So it's for this reason that you should always work out the complementary solution before going after the particular solution. Because if you work out the particular solution first, you might have the problem of a term from the particular solution already being represented in the complementary solution, and therefore your coefficients aren't going to match up the way you want, as we saw with that 0 equals 3e to the x, which doesn't make any sense. So always go for the complementary solution first, then go to the particular solution, and once you've written out the trial, if you see any repeated terms from the complementary, then you need to just throw in an extra x factor in those particular ones, so there's no repetition. Okay, so I think the best use of our final few examples is just to practice writing down the trial particular solutions, meaning the forms, so without actually working out all the coefficients, because that's just mechanics. So I'd like to draw your attention to the table at the bottom of page 146 in your textbook, which has a bunch of trial particular solutions for various forms, or as your ebook edition would call them, triaticuatia. I think until you really get the hang of the pattern that's happening, having a table like this at the ready for working out these types of problems would be a very good idea. All right, so with that in mind, let's take a look at the form that we have on the right-hand side of this differential equation and see what the form of the trial particular solution would be. So to properly answer that, we are going to need the complementary solution. So of course we've worked with this guy several times, and we know that the complementary solution is c1 e to the x plus c2 e to the negative x. Because this right-hand side has e to the 2x and not e to the x or e to the negative x, we're in no danger of having any repeated terms. So we don't need to do any of the magic where we introduce an extra x factor. So that's nice. Okay, so to find our yp, we should probably factor the e to the 2x out so we can kind of group this as a polynomial times an exponential. And that helps us break it down because our particular solution will be of the form of a polynomial multiplied by the exponential. And the polynomial here will be the most generic version of this polynomial, so that would be a cubic, which would be ax cubed plus bx squared plus cx plus d multiplied by the exponential e to the 2x. And that would be the form of our particular solution. All right, what if we had the same left-hand side, but this time our right-hand side were something like this? Well, again, we have the same complementary solution, so we should acknowledge that. And note that we're in no danger of repeating those terms because we don't have an e to the x or an e to the negative x in our right-hand side. So let's note that we have here a polynomial, we have exponential, and we have another polynomial here. And you might think, well, maybe we could factor like 3x squared out and sort of get a polynomial times an exponential, but you'll still have a leftover polynomial when you do that, right? So it's actually easier in this case to leave it the way it is and simply to write that our particular trial solution here is going to be the polynomial, the 3x cubed. Well, its most generic version is ax cubed plus bx squared plus cx plus d. And I think we're going to need a little more horizontal clearance. So let's move this guy maybe right there. Then we're taking that, we're multiplying by the e to the 2x. And now we're adding the generic form of this polynomial 6x squared, which would be something x squared. What's our next letter? So capital E, x squared plus fx plus g. And there's the form of our particular solution. So we would have 7 variables to work out if we were to do this one all the way down. All right, now let me just modify things. Let's go into the second case. What if we had something very similar, but instead of e to the 2x, we had just e to the x? So everything's the same as the part B example, except for that fact. Well, remember, our complementary solution is this guy. And if we start to set up our particular solution, we would get, say, basically what we had last time. It looks very similar to what we had last time. The only difference is that e to the 2x is now just e to the x. So let's just ignore that. Let's put our e to the x here, but let's ignore the fact that it's repeating a factor from the complementary solution, just for a moment. Okay, so is it really? Well, yeah, if you distribute this e to the x, then the d e to the x is a repeated term of c1 e to the x. So the only way around this is actually what you might think, which is just to put another x in front of that guy, like that. And suddenly, that completely solves the problem. Okay, let's look at a few more. Okay, what about this one here? Well, again, we have our complementary solution. So we need to avoid those, but I don't think we're in danger because we're back to e to the 2x here on the right. So what have we got? Well, we have a linear factor, we have an exponential factor, and we have a trigonometric factor. So remember, when you've got the trigonometric factor on its own, you would get the form like a cosine of, in this case, 3x plus b sine of 3x. But instead of a and b, what's going to go in front of those is the form for x e to the 2x. So that would be a linear. So we have y p. The x, which is a linear or first power polynomial, produces the form ax plus b. Then we have our e to the 2x. And we've got our cosine. And we'll just do this again, but with a sign. So we'll have not ax plus b. I guess it'll have to be cx plus d. E to the 2x. Sine of 3x. And there we are. That's the form of our trial solution. Okay, what about this one here? Y double prime minus 2y prime plus y equals e to the x. All right, well, finally we have a different complementary solution to work out, so let's quickly do that. So auxiliary equation here is m squared minus 2m plus 1 equals 0, which is, of course, m minus 1 squared, giving us m is equal to 1 twice. So that means that the complementary solution is c1 e to the x plus c2 x e to the x. Now we can finally put our attention toward the particular solution. And, well, we would sort of want to go just a e to the x, all things considered, except, well, that's repeating this term right here, so no problem. We'll just solve that by putting an x here. And all is wonderful with the world. Oh no, that's now repeating this term. How will we ever make it through this problem? Of course, I'm not a good actor, but there we are. Ax squared e to the x is exactly the guy that we need. That's going to work. So just keep introducing, like I said earlier, higher powers of x so that you're not duplicating any of the terms from the complementary solution. All right, we'll do one more. Same left-hand side. And this time the right-hand side is something like 6x plus 2 e to the x. So again, our complementary solution is still c1 e to the x plus c2 x e to the x. And our particular solution, we would say, well, let's make this ax plus b e to the x. That's sort of where we'd start from. But we're actually repeating both of them, because if you distribute that e to the x, you're going to get a times x e to the x, which repeats this term, and b e to the x, which repeats that term. So we can get around that by introducing that x factor, of course. And does that work? Well, we're no longer repeating the c1 e to the x, but we're still repeating the c2 x e to the x. So we're going to go up to x squared again on this one. And there we are. Okay. So some closing remarks. The method of undetermined coefficients only applies if the right-hand side consists of a polynomial, an exponential, or sine and cosine, or sums and products of those things. Okay? If you look back at the table, you'll see that it only consists of that particular type of function. And why is that? Because those are the functions that, when taking the derivative of them, they don't leave their little ecosystem, right? So polynomials will go down to polynomials when you take their derivative. Exponential functions will stay as exponential functions, and sine and cosine will go back and forth between each other without changing the power. To handle a wider variety of right-hand side functions, we're going to need some bigger tools, and we're going to see those in the next section with a technique called variation of parameters.